with the presence of Professor S.R. Gandhi Sir, Director of SVNIT Surat. Professor S.R. Gandhi Sir is a renowned academician and administrator. He is a professor at Civil Engineering Department, IIT Madras. Under his vibrant leadership, SVNIT has achieved many significant milestones like NIRF rankings for its academic performance and infrastructure, promoting industry and institute interactions, and providing pleasant research environment to the students. He has been awarded his PhD degree in Geotechnical Engineering from IIT Madras in 1985. His areas of research interest are pile foundation, ground improvement, field instrumentation and monitoring, fly ash utilization and disposal facility. Under his guidance, 5 doctoral theses have been successfully completed. He has more than 22 years of teaching experience. He has authored many papers in various international journals. He has also taken an active role in Geotechnical Society. Apart from teaching and research, Professor S.R. Gandhi Sir has been an active consultant, advising various government and private organizations in design and analysis of foundation for various projects. Thank you, sir, for gracing this program with your valuable presence. I would like to invite you to address the participants.
A very good morning. Thank you, Dr. Vanna, for the kind words of my introduction. Namaskar to all. I am happy that sure that he will have occasion to visit us soon and interact with you all in person now that the situation is improving day by day. Professor V.H. Pradhan, Chairman of the event, Dr. J.S. Dodia, Co-Coordinator of the program, Dr. Saroj Yadav, faculty colleagues in Mathematics Department, all the participants to the program, research scholars. I warmly welcome you all to the inaugural session of this advanced analysis and numerical techniques to solve the differential equations for various engineering applications, which is being held from 29th September to 3rd October. Now, as Vandana has informed that I have the geotechnical background, and this subject also even with a hammer down into the ground. So we do stress wave analysis. It's based on the famous Smith's equation, second degree differential equation. Then we have consolidation theory to estimate the settlement of the foundation that also needs a second degree differential equation to be solved to know what will be the rate of settlement when the structure is built on the ground. The flow lines, equipotential lines, and there are n number of applications of differential equation. And I cannot imagine that if you don't have a good software and solution for this differential equation, how this analysis would have been possible. The finite element analysis, again, used largely for various applications. It also solves these differential equations, particularly when we talk about nonlinear analysis also. As informed by Dr. J.S. Dodia, the AMHD faculty has been very active with good contribution to the research and publications with a high H index, as we have informed. And also the student has a good placement. We get very good student for a PDF also in the mathematics department, and our faculty has also gone abroad under various schemes. This year we are celebrating as our Diamond Jubilee celebration, and we have organized 50 plus programs for various in all the departments. And this happens to be one of them as part of our Diamond Jubilee program. I congratulate the coordinators for organizing this in spite of many odds, which I will be discussing little from now. As a part of Diamond Jubilee celebration, the Institute has also planned to install a statue of Sri Ramanujam because the world is celebrating his 150th birth anniversary, and Department of Mathematics has a plan to install a difficulty on the campus because the weather is quite bad here. Last 3 or 4 days it has been pouring continuously, and there's a forecast to have rain for another 2 days. And this has resulted in frequent interruption of the power of the network. And I could not join for the inaugural program from my house because there was no network at home. So I had to rush to the office to connect. But still, in spite of all this odd, both Dr. Saroj Yadav and Dr. Jodia and the leadership of Dr. Pradhan has carried out all the requirements for this program. I am sure the participants will be highly benefited by various lectures that has been planned from experts. And Professor Chali Sajari has been our chief guest and also helping the department at various stages. I thank again Professor Chali Sajari for the support, and we look forward for your visit here. I will not take much of your time because you have a heavy agenda. So I wish all the participants a very fruitful and useful deliberation in the event and sweet memory of this program. I'm sure the program will be arranged year after year, and you will be uh, having the opportunity to participate again. Thank you very much. Namaskar.
Thank you, sir. I am also delighted to introduce our honorable chief guest of this program, Professor Dimal Kumar Chalisazar, sir. He is a colonel and professor of applied mathematics at Virginia Military Institute, Virginia, USA. He has served as a director of study abroad program, chair of international program committee, and member of liaison committee. He has completed his PhD in 2005 from IISc Bangalore and University of Baroda. He has more than 24 years of teaching experience. His research specialization is on control theory and applications through functional analysis. He has published 6 books and more than 54 research papers in peer-reviewed international journals. He has given more than 60 presentations in the conferences, including invited talks with 1 monogram. He is the editorial board of 11 journals and reviewer of more than 25 journals. He has reviewed more than 120 research articles for peer-reviewed journals. He has supervised 6 PhD theses, 15 students for graduate and undergraduate level independent research, 1 capstone project, and 1 honor thesis. He has been awarded by various organizations for his excellence beyond limits. Your presence in this program is a great motivation and inspiration for all of us. We are really delighted to have you here, sir. Thank you for joining with us. Now, I would like to request you to address the participants.
Thank you, Vanna, for nice introduction. Professor Gandhi, Dean of the Faculty, Dr. Pradhan, Dr. Jayesh, Dr. Saroj Yadav, Dr. Vandana, all faculties of different universities and participants. First of all, I would like to congratulate you guys for the Diamond Jubilee year. I just got the introduction of the participants and I figured it out that so many of you are just pursuing PhD, or so many of you, they are just going to start the PhD program. So today I would just like to talk about the motivation for the further study, for the contribution, how you can give your best. I don't say like Napoleon that there is no impossible word in my dictionary, but I would like to go further and I would say that impossible is possible. Always keep in mind this thing, impossible is possible. Plenty of examples are there. Before 20 years, before I would say 10 years, there were $10 million problems in the world, which were not solved since number of decades. But now one of them is solved just last year. The previous one was solved in 2012. So impossible is possible. Always keep in mind this thing. Just make it happen. There is a light inside of every one of us, an ember that burns and begs us to become more than what we have ever been. This is the flicker of creativity, the spark of an idea, the outline of a design. You get to make it happen. Can't nobody else do it for you? You are in charge of your it. Every day the clock is ticking. Every year the calendar moves. Your it cannot be delayed further. Your it got to start with your first step. Your it got to start with your first move. Matter of the fact, it begins in your mind. It is your dream. It is your purpose. It is your future. Give your 100%. Try to do your best. Try to utilize your time. If you respect time right now, time will respect you in the future. Just trust me. This is the experience of my life. If you respect the time, time will respect you. There are three types of people in the world. There are people who watch things happen. There are people who wonder what happens. There are people who make things happen. Now you have to decide. You got to determine which person you are. You could make a wish or you could make it happen. You first believe that you can, then you will, then you must. There is an inner fire inside all of us, inside you. After everything you have been through, you have got to be able to see your value. Put aside all your doubts, all your frustration, all your weaknesses, all your fears, and be strong enough to go forward. Again, put your 100% in the field and be honest to yourself. There is no one like you in all of the world, in the earth. There is no one that can do what you can do. You are the only option. You are the only one that is going to be able to do this thing. It's time to rise up. It's time for you to make that first step to make it happen. There are some tools like persistence, consistency, resilience, courage, establishing your priority, mastering self-awareness, maintaining focus, believing. Use these tools. This is the hope that strokes your patience. It's our aspiration that must become your allies. So guys, please keep in mind this thing. Try to take the advantage of all these 5 days. All these, Dr. Saroj Yadav and the team, Dr. Pradhan, Dr. Jayesh, Dr. Vandana, they are trying their level best to help you out. Try to take the advantage of these 5 days. Give your 100%. If you have any doubts in problem, I have a YouTube channel too. I'm going to put my lecture on YouTube. You can go through the lecture whenever you want. And if you have some doubts, just send me the email. I will try my best to reach to you as soon as possible. I'm just trying to help you out. Thank you so much and good luck to all of you. Thank you so much. And thanks for the invite.
Yeah, thank you.
Thank you very much, sir. We are also honored with the presence of Professor Kasi sir. He is a professor at Department of Mathematics, NIT Warangal, Telangana. We are really delighted to have you here, sir. Thank you very much for gracing this program with your presence. Now, I would like to invite you to address the participants.
Hello.
Hi, yes.
Yes, sir, you are audible.
Yes, sir. Your voice is audible.
I'm audible. Yeah.
Yes, sir.
Yeah.
Yeah. So first of all, I would like to congratulate the organizers, Professor Pradhan and his team, Dr. Saroj Yadav and Dr. Jayesh, for conducting this type of the STDP in the pandemic situation. So I wish you all the best, and I hope that the participants of this STPP will get the benefit from the lectures given by the speakers. So thank you one and all.
Thank you, sir.
Thank you, sir. It is my privilege to propose the vote of thanks on behalf of the Department of Mathematics and Humanities. So, on this occasion, we would like to express our gratitude to SVNIT and CCE section for giving us such opportunity to coordinate this program. We would like to thank the Director of SVNIT Surat, Deputy Director of SVNIT, and Professor Dimple Kumar Chalis Hazar, sir, Chief Guest of this program. Thank you very much for giving your valuable time. On behalf of the organizing committee, we would like to thank all the participants for their kind support and cooperation in making this program a resounding success. Finally, we would like to thank all our faculty members, research scholars, and non-teaching staff who helped us to organize this program successfully. Thank you everyone for giving us your precious time and gracing this program with their valuable presence. Thank you very much. Have a good day. With this, we end up with our inaugural ceremony of this program. Thank you everyone.
Thank you so much.
Yeah, thank you. Vanna, now you just announced that we'll have 5 minutes break, and after that we will begin with the keynote.
Okay, sir.
Yeah.
So we are having a 5 minutes tea break now, and after that we will gather for the keynote address by Professor Dimple Kumar Chalis Hazar, sir. Thank you everyone.
Thank you.
Can you see my screen?
Yeah, it is visible, sir.
Yeah.
It is visible.
Visible? Okay.
Yes, sir, it is visible.
Yes, sir.
Thank you so much.
Yeah, Pradhan sir is there.
Hello. Yeah,
Yes,
I
sir.
think, shall we start now?
Yes, sir. Yes, sir.
I'm ready.
Yeah. Yeah, Vanna? Dr. Jayesh, I think we will just invite Sir to begin.
Yes, sir. Yes, sir. Yes, sir. Sure. Good morning, one and all present at here. At the keynote speech of this program that we are going to hear, and for that our chief guest of the program, Professor Dimple Kumar and Chalisaja sir with us. Sir, I requesting you, you can please say, please start.
Thank you so much, Dr. Jayes, for the
Yes.
invite. And now we are going to start. Without wasting time, we are going to start the today's lecture. Topic of my today's talk is exert and trajectory controllability of semilinear impulsive neutral functional differential equations within finite, usually we say infinite delay. And I would like to stay with the conference theme. Conference theme is analytical and numerical differential equations. So that's the reason I selected this article. So we are going to see the analytical methods as well as the numerical approach of the problem. Again, thanks for the invite, and let me start my talk. The outline of the talk is like this. First of all, I just would like to give you the introduction of the problem. Then after how I was motivated to learn this problem, some preliminaries are required to go further in the problem. And I would like to provide you one new definition of the phase space, which is required, which is essential for the delay part, delay differential equation. Then I would like to switch over to the controllability theorem, controllability problem. And then after, we will be switching over to the new theme that is called the trajectory control. We are going to start with the very basic things of the trajectory control in a scalar field, scalar problem. And then after, we will be switching over to infinite dimension space. And then again, as an example, we'll come back to Rn, finite dimension. And some examples are there with numerical estimations. That's what we are going to see. So this is then after I would like to give you some new development in the field of this trajectory controllability and some recent problems and open problems in the field of trajectory controllability. And some references, of course. All of you know these things, that control problem is one of the most diversified application of differential equations and partial differential equations. You can see over here, so many times I've explained this thing, that suppose we have one warplane moving in the air, and suppose we want to hit this warplane with the help of the missile. That means we can, this missile can hit the warplane exactly over here. You can see this yellow spot exactly over here. And if missile hits the warplane exactly the exact target decided here at the yellow spot, that is called the exert controllability in the infinite dimension space. But you can see over here, both are the moving objects. So sometimes, or most of the times, it is quite impossible to get the exert controllability, to get the target exactly over here, the desired point. But it could be possible that your missile can hit the warplane in the neighboring point of this yellow spot. So that is called the approximate controllability. There are some different notions of controllability, like null controllability, optimal controllability, then fuzzy controllability, then you can say for partial controllability. So different notions of controllabilities are there. We are going to talk over here about the exert controllability, and then after the more detail or more stronger notion as a trajectory controllability. So let me consider this problem. You can see over here, this is d by dt of x is just the first order problem, but here is the delay part, and here we have delay parts. We have delay part on both the sides of the problem, and that's why it is called the neutral problem. And it neutralizes the system on both the sides. A is the infinitesimal generator of an analytical semigroup T of t greater than 0, that is always bounded in a Banach space X. U is a control function lying in L to J to U, a Banach space with admissible control function with U as a Banach space. B is a bounded linear operator from U to X. This is the nonlinear operator from the interval cross phase space, because whenever you delay part, always you need to decide some phase space. Delay part means, let me just explain to you what we mean by the delay part. There are two types of delay. One is finite delay, another is infinite delay. Suppose something is going on, since last, I would say 2 days or 3 days or 1 year or 2 years like this. But we know the exact time when the system started. And now we would like to give the control at this point, at this moment. So this type of notion that is called the finite delay. So whenever, because we are moving on the negative part of the time, I mean to say below 0. So 0 to negative side, I would say, suppose let me fix negative r to 0. So we have to fix one space over here, and that is called the quotient space. But in particular, I would like to consider this as the phase space. But there is another problem that is called the infinite delay. Infinite delay, I mean to say that we never know when the process started. We never know. That doesn't mean that the problem was started long back before 1,000 or 2,000 or 5,000 years back. That's not the concept. That's not I mean by infinite delay. Infinite delay means we don't know the exact time with second and millisecond. We don't know this thing. As for example, suppose someone goes to the doctor for routine checkup and in 2020, and suppose he was not detected diabetic. But in 2021, when he went to the doctor at that time, just before a month, suppose somebody went to the doctor and now doctor said that now you are diabetic. Now you never know when the diabetic process started in the body, exactly at what time. You never know, because it could be maybe last year he went to the doctor in the month of suppose June or July. And then after diabetes started in the month of August, September, October, December, January 2021, we never know. Nobody can predict this thing. Even doctor cannot do this thing. This type of delay, I mean to say that's the infinite delay in which time period is not predicted, is not decided. And we need to make, we are working with this type of time delay, which I would like to say infinite time delay. And we need to define another phase space. The motivation for this one is like this. Actually, I was reading one of the literatures, and based on the phase space and the delay portion, delay differential equation. And I came to know, I was reading the book of Hino Murakami and Naito, and they mentioned this thing, that if you are working in the finite delay, in that case, you can use the generalized definition given by Hall and Kato. That's what people have been using since number of years. But I'm wondering why people have not gone to this book. When I went through this book and I realized this thing, that what people have been using, that is actually wrong. And then after I just proved my first result, I developed the phase space for the infinite delay. And that paper was published in JOTA, Journal of Optimization Theory and Application, Springer. And then after, it was welcomed by most of the big sorts in control theory, big control theorists, they welcome that paper. And nowadays, some of them, they are using this space. My space is the generalization of the space given by Hall and Kato. And that was motivated by the Hino Murakami and Naito's book. So that is one of the motivations for this lecture. So just keep in mind this thing, that what we mean by the phase space and why, what is the requirement of phase space, how I was motivated to learn this problem. That's what I explained to you. And after, you can see the phase, this is delay portion. Here it is infinite delay. So I'm starting with negative infinity to 0 to x. And this is xt is theta equal to x of t plus theta. And these are the nonlinear functions defined like this. The impulse term is given like this, xtk plus minus xtk minus, represent the jump of the function at x, function x at t equal to tk. And motivation already I explained to you. So let me just skip this part. And now I would like to go through the preliminaries. We have very limited of time because I would like to give you lots of things in this 1 hour. So please pay your full attention. If you have some doubts, please keep your doubts aside and we will discuss at some other point of time. Definition of piecewise continuous function, let collection of all functions w, or you can say omega from 0 to b to x, such that w is continuous at t is not equal to tk, and wtk minus is equal to wtk, and tk plus wtk plus exist. And this piecewise continuous function, this space is endowed with the uniform convergence norm in Banach space. And I would like to consider this wt as w tilde wk tilde t, that is equal to this one if t lies in tk to see each of these intervals. Suppose k equal to 1, so it is t1 to t2, t2 to t3, t3 to t4, like this. In that case, I'm going to get the value wt. Otherwise, if t equal to tk, this endpoint, left endpoint, my value is wtk plus. And respectively, I can define ek tilde wtk. Wk tilde w belongs to E, the Banach space. And based on this one, this Ek tilde, I would say that let E is contained in a piecewise space of piecewise continuous function is relatively compact if and only if Ek tilde is relatively compact in each of the subintervals, space of continuous functions from the subintervals to the Banach space X. This is the phase space I developed. And you can see, if you want to look at the proof, I have not considered the proof over here, but if you are interested, you can look at my paper in JOTA and you will find the full proof of this one. So BH, collection of all functions phi from negative infinity to 0. Just look at over here. I consider just negative part, negative infinity to 0 to Banach space X, such that phi theta is bounded, measurable function on negative R to 0. And I have taken R is greater than 0. That means you can take R equal to 2, 3, 4. But actually, because of this negative sign, you are moving on negative part. So negative 2, 3, 4, 5, 6, negative million, trillion, so on. And this integral condition is satisfied. Integration hx supremum of phi theta is finite. And this space that is endowed with this norm of BH equal to this one. And obviously, this is very easy to prove. Those who are the beginners in the field of I'm saying the research field, they can just prove this one. This is a Banach space. What you need to do, just take the Cauchy sequence and try to prove the convergence of the Cauchy sequence in the same space. And Cauchy sequence convergence in the same space means this is a nonlinear space. And if Cauchy sequence is convergent, means a complete space, and complete nonlinear space is a Banach space. That's the well-known thing and very easy to prove. I leave it to you. I need one more space, that is script B of B. That is a collection of all x from negative infinity to B to x, such that xk is in the space of continuous functions from jk to x, and x restricted on the interval is a piecewise continuous with this condition. This is the phase space given by Hall and Kato, that xt belongs to, xt means delay part, x suffix t means always delay part. Just keep in mind this thing. Xt belongs to my BH, space BH. BH, I mean to say this space, this BH. Okay. So xt belongs to BH. Actually, that BH is defined over here by Hall and Kato, but we would like to go for the generalized BH space, generalized phase space. And my function xt that is bounded by this norm of xt, and norm of xt that is bounded by this subnorm. H greater than 0, km, they are the functions from 0 to infinity to 1 to infinity. K is continuous, m is locally bounded, and they are independent of x. We are going to use over here, and one more thing, this LXTB0 that is less than this inequality is satisfied. We are going to use this inequality in our proof. And I am going to use over here the Skaffer's fixed point theorem. The theorem says that let D be a convex subset of a Banach space X. Assume that 0 is in D, null vector, and let F function, nonlinear function F from D to D be a completely continuous map. Completely continuous map means you need to use over here the Arzelà-Ascoli theorem because you are working in infinite dimension space. Just keep in mind this thing again for the beginners. Those who are working in the field, they know it very well. But for the beginners, those who are pursuing PhD or those who have just started before a couple of years like this, whenever you have compactness, compact implies closed and bounded, but closed and bounded does not imply compactness. That means whenever you are, that is in infinite dimension space. For finite dimension, converse is true either way. So you don't have any problem. But in infinite dimension, compact implies closed and bounded, but closed and bounded does not imply compactness. That means we need to rely on some other thing, and that is called the, thanks to Arzelà-Ascoli, or Ascoli and Arzelà, they have given really fantastic proof, and that is called Arzelà-Ascoli theorem. It says that if your map is, or functionals, if your map is equicontinuous and relatively compact, not compact, but relatively compact, in that case, that map is completely continuous map. And every completely continuous map that is compact, the space is compact. Then the set collection of all x in D such that x is equal to lambda fx, lambda lies between 0 and 1 is unbounded, or the map f has a fixed point. I am going to prove that this my map f, whatever I am going to fix my f operator f, that is bounded. So this will be gone. That means only f has a fixed point in D. That's the only portion left out, and that's what I need. For this, I require some of the assumptions. Whenever I say Lx, it is to be understood that I'm talking about the Banach space from x into y, but when x and y are same, I would like to denote by Lx. A is the infinitesimal generator of an analytical semigroup T of t. T of t is bounded by some constant m1, and negative a to the power alpha. Alpha lies between 0 and 1. You can see over here, the fractional order. Alpha lies between 0 and 1. That's endowed with this norm of x alpha equal to this one. This, I have one embanding, gamma 0 is less than, gamma is less than or equal to eta is less than 1. Then x eta is the Banach space, and x eta to x gamma is a continuous embanding. The function s from negative a to the power eta ts is continuous in the uniform operator topology, and there exists constant cn greater than 0 such that this norm of a to the power and tt is bounded by this one. I will let you know where we are using this one. My function f satisfies the Carrier theory condition. Carrier theory condition, that means function is measurable with respect to first variable. You can see over here first variable, and it is continuous with respect to second variable. So that is called the Carrier theory condition, well-known condition. And my nonlinear function f norm is bounded by this functional wf norm of psi at ph, where t and psi that lies over here. This psi means it is the delay part. Psi is a delay part because my nonlinear function involves the delay portion. Xt was there. That xt I have denoted over here as a psi. Okay, for every x from negative infinity to b. Now I'm moving, not negative infinity to 0, but I'm moving on my right side too, because now I would like to give my control. So negative infinity to b to x such that x0, initial condition, that is in bh, and x restricted on j, that is on b of b, and the function t, g function, because it is on the other side of my equality, and that's why I would like to consider this one as negative a to the power beta g of txt is continuous. And this has the norm. It is bounded by some function c1 and c2 like this. And L is equal to whatever L c1 is less than 1. This L actually defined in this way. That was the condition, one of the conditions in my phase space. I'm sorry. One of the conditions in my phase space. Okay. And I have just relied on very standard technique of Quinn and Carmichael to get the invertibility of my operator W, L2 to X alpha. And this invertibility of the operator, that is nothing but in the quotient space. And that is bounded by some constant M3, and operator B is bounded by constant M2. M1 is the bound of my semigroup. Okay, I need one more estimation. That's what I have just used over here. And now I'm in a position to write the mild solution of my system, my neutral infinite delay system, and its mild solution. Mild solution, I mean to say that if you are not aware of this terminology, then I request you to refer the book of Pazzi. Very nice book is given based on semigroup and its applications. Chapter number 4, in which this mild solution, strong solution, classical solution, all the definitions are given. It's a very fantastic book, very, very well-known book, and every control theorist is having this book, hopefully. A function x from negative infinity to b to x is a mild solution of my problem 1 if my initial point x0 is in phi and xt restricted at j, that is in bb, and that is equal to this one. Xt equal to tt phi 0 g0 phi g of txt, and this one. This is my control. Keep in mind this ut. I am going to work with this u. And this is my nonlinear term, and this is my impulse term. Control definition varies from system to system. With respect to this system, my control definition is like this. The system 1 is said to be controllable on the interval j if any initial state x0 and final desired state x1 in the Banach space x, there exists a control u in L2 such that the mild solution, this xt, satisfies xt equal to x1. See here, I started with x0, initial point, and now it goes to, it hits the target, xt equal to x1. And the condition, this initial condition, as well as these impulse conditions are satisfied. I require one more space because I already defined x from negative infinity to b to x. I would like to consider collect all these functionals, and I would like to give the name b beta 0, which ended with the norm x at b. Whenever b is there, I just would like to write b. So x at b, that is equal to this one. So that is bounded by this sup norm. And I have one more estimation, xt plus yt is bounded by this one. That's fine. That is easy. So now my main controllability result. You can look at over here, guys. The first assumption says that for each r greater than 0 and all epsilon greater than 0, there exists a compact set u epsilon r. You must be wondering that why I wrote it down compact set over here. Let me just introduce a little thing over here. In 2008-9, when my first research students was working with me at that time, we faced one problem. That was the crucial years for not just us, but for all the control theorists, because before 2008 and 9, people used to take the assumptions of the compactness of the semigroup or the cosine operator. But thanks to Trigiani, Dr. Trigiani, University of Virginia, just 50 miles from here, he proved one result long back. And he said that if you are working with the assumptions of the compactness of the semigroup, that means you are no longer working in the field of I mean, say in infinite dimension space, you are falling to finite dimension space. That means, and he proved that result in 1979-80. So 1980 to 2009, almost 29 years, whatever the results were proved in the literature, all the results were wrong based on infinite dimension space. Infinite dimension space actually started in 90s. So I would say mainly almost 19 years, plenty of results were proved, and big sorts, big control theorists, they accepted this thing that the results were wrong because they assumed that assumptions of the compactness. I have dropped that condition over here. And my first research student, we work with the same thing. The whole thesis that is mainly based on the non-compactness of the semi-group. So we got the breakthrough. Anyway, so here you can see U epsilon, that is the compact set. That's fine. I said my semi-group should not be compact, but it could be possible that my nonlinear function f is compact. Suppose f is compact, this is closed image of a compact set is compact. And that's the reason that TTF S psi that is in U epsilon r. So that's the reason I said that this compactness that is in X. So I hope that is clear to all of you. There exists a positive constant LG, LK, and this condition is satisfied. You can say kind of the Lipschitz continuity, and Lipschitz continuity over here for the impulse function, IK, psi1 and psi2. And this estimation 1 plus this long estimation, this constant is less than 1. Under these assumptions, I'm going to prove that system 1 is controllable. I have considered my control U mainly for my system. So whatever the mild solution I gave it to you, this is the mild solution. I told you that I'm going to work with this control U. Whatever the control I have chosen, I'm going to plug that value over here for this control. So my length of the equation will be really very long, and I would like to give that name as my operator phi. So whatever control I have, I decided over here, we can fix this control by working 157 steps or like this. That's easy to prove. Control theorists know this thing. Plug this value over there over here in US. This is my control U. And I have given the map gamma like this. And this map gamma has a fixed point. If I prove this fixed point is then a mild solution of the system, which implies that the system is controllable over the interval 0 to t. Okay, so my first claim is gamma BR is contained in BR. I would like to prove the result in a negation way that suppose this is not true. This is not true. That means there exists at least one function over here in BR, which is not a part of this space. So you can see over here. So there exists at least one function XR in BR, but XR is not in gamma BR. That means my gamma XR TR is greater than or equal to R, means R is less than this one. Let me use this one. Let me use this gamma operator over here. Let me use my assumptions. After all these assumptions, I'm going to get this R is less than this one. And finally, if I divide throughout by R, both the sides, I'm going to get this estimation. But what is this? I have assumed that this part must be less than 1. Here it is greater than 1. So my assumption is wrong. That means whatever I assume that given thing is not true, I was wrong. That means given thing is true. So that's the way I have just proved. There are different ways of proving. Then after I have just take the decomposition of my map gamma in gamma 1 and gamma 2. In gamma 1, I consider all my things without nonlinear functional. Nonlinear operators I consider with gamma 2. So gamma 1, that is just I need to prove the contraction mapping. If I prove the contraction, gamma 1 is done because there is no nonlinearity over there. But gamma 2, we have to be very careful. Gamma 2 is completely continuous operator. For complete continuity, first of all, I just would like to prove the equicontinuity. You can see over here, gamma 2 xt plus gamma. Equicontinuity is a very strong concept of continuity. Please keep in mind this thing. So gamma 2 xt plus gamma minus gamma 2 of xt. And if you use 0 to t plus 10 and all this thing, finally, I have proved that this one, you can see here, there exists for any epsilon greater than 0, there exists delta greater than 0 such that t of t minus I, this estimation is less than epsilon for 0 is less than or equal to tau is less than delta and x belongs to BR, and gamma 2x minus gamma 2y that satisfies this estimation that is bounded by this one, and therefore gamma 2 BR that is contained in B0 is equicontinuous from the right of t or tau. So equicontinuity is proved. And next I have proved the relative compactness. Relative compactness of gamma 2 that is proved like this. You can see here, this is the relative compactness, and equicontinuity plus relative compactness means my gamma 2 operator is completely continuous So it is a completely continuous, and that's why gamma is a condensing operator, because every completely continuous operator is a condensing operator on my space BR, and that's why it is a fixed point. It's copper fixed point theorem that is satisfied, and that's why the proof is complete. And I just took the wave equation as an example. You can see here my wave equation with particular values, and whatever the Banach space I have chosen in general, I could take this one as my L2 space. It's a Banach space, Hilbert space. B endowed with the usual norm, and my infinitesimal generator A, domain of A is defined like this: collection of all omega in X such that omega and omega dash are absolutely continuous, with omega dash double dash is in X, and this omega 0 and pi that is equal to 0. This condition is satisfied. This infinitesimal generator that is given in particular form, summation of n square inner product omega, omega, n, and omega, and my semi-group that is kind of Bessel function over here, and my invertible operator that is like this, BUT, and this invertible operator W inverse T that is defined like this. Under this, whatever the assumption, all these assumptions, whatever I assume in my theoretical portion, they are satisfied one by one. You can see here that's condition 1, condition 2, all are satisfied, and that's why I can say that whatever the heat equation I have assumed as a practical example, that is the formulation, system 1 is the formulation of my given example, and that's considered the example, and that's why it is controllable. One can prove in the same line the second order equation, the second order of x dash t, g of t, x t. Look at here, I just made the changes over here. That doesn't mean that you can use the transformation and try to convert your second order to first order and then first order to mild solution. No. Fitzgibbon in 1992, English engineer, electrical engineer, he proved one result, because mathematicians and control theorists, electrical engineering, those who are working in control field, they are correlated. They are just, I would say, two sides of one coin. Frequently, mathematicians have to take the help from the engineers, those who are working in control, for the practical problems, and vice versa. Whenever they are facing some problems, they come to us for the mathematical solution. Anyway, so Fitzgibbon, he proved this result, and he said that if you are using the transformation method and try to convert the system to first order, then mild solution, you are losing the control. He proved this result. That means that problem remained unsolved for almost 10 years. In 1999 or 2001, two mathematicians, they got the breakthrough, and they said that you can work with the sine operator and cosine operator. But still, I have one question. That's the open question for all of you. Please pay attention over here. This is, of course, second order problem. System components are given over here. I don't want to go into detail of this one. This is the definition of cosine operator. And with the help of this cosine operator, you know this thing. I have defined the sine operator. It's not just sine function, it's sine and cosine operators. Now, once I say that this integration of cosine is sine operator, what is the relationship between my semi-group and sine operator? I asked this question when I was doing my PhD to my supervisor, and I could not get the proper answer. Even today, I don't get the proper answer, but people consider this thing that sine operator is as good as the semi-group, but I don't find any proof in the literature. If you find something, please let me know, but I don't find this thing. Still, that's a question for me. Anyway, I'm very honest based on this one, so that's why I don't feel any shy to discuss the same things with you. Anyway, guys, that's fine. And this is the mild solution in terms of sine and cosine operator. And now you can go along the same line, same terminologies, whatever I've done previously, and you can prove the control result over here too. Now I would like to consider my trajectory controllability. So trajectory controllability, introduction is done, that's fine. Now, usually what happens, guys, look at over here. First of all, I just would like to give you the motivation. Usually what happens that you have this initial point and this is a final desire point. And if you give the control to your system at the initial point, that system may move like this, it may move like this, it may move like this, it may move like this. It chooses any of the path. We don't know. We never know what path the system is going to choose. And when I was working on the field of control theory, I was just wondering how it is possible without knowing the path, how it is possible that one can work with the system practically. Because suppose you want to hit the warplane with the help of the missile and you don't know the path, it's going to hit the target. But without knowing the path, it's ridiculous for me. So that's why I just try to develop the new thing, and that is called the trajectory. Because once you know the trajectory, once you know the path, there are two benefits. There are two advantages. The first advantage is you can minimize the cost involved in the system, and that is highly useful in optimal controllability. And the second thing is you can safeguard the system. Suppose some mountain range is there or some obstacles are there, you can change the direction of the system. So there is two advantages are there, and these two advantages motivated me to learn the new concept of control theory that is called the trajectory controllability. Because there's a new concept, I just would like to consider the very simple scalar system x dash t equal to atxt plus b of t ut plus f of t xt. And this one, I have not considered any delay portion over here because that is just a new concept. I wanted to make sure that this new concept works just for the scalar system, and then find infinite dimension space, other spaces. Then after I can take care of that delay or other portion. These are the system components. At is in L1 function and j is 0 to t. B is an operator, j cross r to us. You can see over here my control is nonlinear and f is also nonlinear. It's extremely difficult. My state is nonlinear. When practically you are going to find the problems like this in which control and state both are nonlinear. But whenever you are working mathematically at that time, it will create lots of hurdles for you, lots of problems for you whenever both of them are nonlinear. So what I'm going to do, I'm going to consider this one has control linear and I can't change my state. So state is nonlinear. And then after I will come back over here with both nonlinear parts. So that's the way I just proceeded further. Okay, so this is just a linear system. So F, G, these are just the components. G is from delta is nothing but T and S from J cross A, because I have one variable, I mean, say, coming from my interval 0 to T, this coming from interval 0 to T, and this is the space R, like this. Complete controllability definition is completely controllable on J if from any initial and final desired state in R there exists a control U in L2 such that the corresponding solution satisfied xt equal to x1. Motivation already we discussed, and now I would like to consider my definition based on the trajectory controllability. Let tau be the set of all functions z dot or zt defined on J. This tau is one function defined on J. That means now this is 0. This is my final desired point. I am going, suppose my system is moving like this. I'm going to consider each and every point of my system. I'm not losing any of the points of the system so that I can come to the exact trajectory, exact path along which my system moves. So z at 0 equal to x0. Look at over here, and z at t equal to x1. So t equal to 1, 2, 3. Every time I'm going to get all the points of my trajectory. System is called T controllable. T means trajectory. If for any z in tau, this space tau now, there exists control U in L2 such that the corresponding solution x squared of 3 satisfies xt equal to zt almost everywhere. Xt equal to zt. Look at over here. This zt is this one, my path, and xt, my state, my solution. Now solution moves along the path. That means it satisfies my each and every point of the path, xt almost everywhere. As I told you that I just would like to consider my control linear and state non-linear. So this is the system. And of course, T controllability, that's the strongest notion of other compared to other controllabilities. My first assumption, my non-linear function f is Lipschitz continuous in second and third variable. Look at over here. This is locally Lipschitz continuous. Weaker notion of Lipschitz continuous, you can say. And under these two assumptions, one can easily construct. This is assumption of set 1. You can say A1 or I1, whatever you want to say. So these two conditions are there. B0 vanishes, F is Lipschitz continuous, and G is locally Lipschitz continuous, weaker notion. And under this condition, one can easily construct the control explicitly and prove the trajectory controllability. For my system, I have chosen my control in this way. Ut equal to z dash t minus blah, blah, blah divided by bt. And if you, my system, if you plug this value in my system itself, atxt plus bt, if bt ut, bt is 1, ut is this one, just plug it over here. So I just plug the value of the control in my system. Now what I did, wt equal to xt minus zt, because xt minus zt, xt equal to zt almost everywhere, that's what I want to prove. That's why I just change my system in terms of wt, xt minus zt. So wt is given like this. And then after, what is this? This wt, I am looking, this system, I am looking for the mild solution, but we are in the scalar field, we are in R, and that's why I don't say mild solution, I would say just a transition function not semigroup, but the transition function phi ts, because we are in this scalar field, e to the power s to t as ds for the ordinary differential equation. So wt, this one is just the mild solution using this transition function. In terms of, in infinite dimension, the same thing would be referred as the semigroup. Okay, and norm in R is just the modulus, so WT is estimated by this one. But what is this? You can see over here, WT was nothing but XT minus GT, and this is nothing but my XS minus GS. So this is nothing but, you can have the exactly same here and exactly same over here. That is nothing but the Grunwald's inequality. So you can use Grunwald's inequality. It's just a constant. So XT minus GT equal to 0 means XT equal to GT almost everywhere, means I'm getting the result. So for scalar field, scalar system, theorem is proved. So now I just would like to go back to my practical problem in which control as well as state both appear non-linearly. I have to make my condition on G little more stronger. Here you can say B satisfies the coercivity of, that is limit t tends to plus or minus infinity, BTU over U, that is equal to infinite. That is coercivity. Operator B is continuous, F is Lipschitz continuous, and G is also Lipschitz continuous. Look at over here. I just made a little strong condition over here. And in that case, my control, system 3 is controllable. Proof is not that simple, guys. My mild solution using the transition matrix is like this. We know this thing. Let Z belongs to tau is a trajectory with the prescribed trajectory with Z0 equal to x0 initial point, and ZT equal to phi of T0 x0. Now I would like to consider all this, not xt. Xt is my state, but I would like to come to my ZT because I would like to go each and every point of the trajectory. So ZT equal to this one. I would like to send everything on left side except my control. My control, I just would like to keep it on right side. And all other things, they are on left side. You can see, just look at my cursor. I'm sorry, guys. It's only 1:15, so I think I have 20 minutes left out, 25 minutes. Okay, no problem. So ZT minus phi of T0, you can see over here, guys, this is I'm mainly I'm worried about my controls. I just kept my control one side, and what will happen? This is differentiable system because very strong assumptions we have about the Lipschitz continuity. So I can go for the derivative. I did that thing over here. And what is this? But look at here. This is my right hand side. If I consider this left hand side as W0 T and this AT phi TS, that is equal to KTS, and WT is nothing but this B of TUT is nothing but WT. So I can write the whole equation in the form of WT equal to KTS WS plus WT. But what is this? This is nothing but the Volterra equation of second kind. And Volterra equation of second kind has a unique solution WT for given WT. It's a Volterra integral equation of second kind. It has a unique solution. It has been proved for W0. Only thing is we need to extract our UT. If you extract your UT, you are done. So and for that, I rely on the techniques given by Damling. Damling, one of the researchers long back, he proved one result based on multi-valued map over here. So consider the multi-valued set function, multi-valued you say in India. So consider multi-valued function G0 to T to R 2 to the power R defined by GT equal to this one. And by my assumptions, I have my GT is non-empty for all T and upper semi-continuous. Upper semi-continuous definition is T n tends to 0 implies GTn contained in G of 0 and ball with center 0 and radius epsilon. Very small ball. And that is a closed ball actually. Further, G has a compact values. And this G is a Lebesgue measurable and therefore has a measurable selection. Once it has a measurable selection, that means we are extracting our GT, and this function U is required control, which steers the nonlinear system along the prescribed trajectory, and hence the proof is over. So I have proved the result for control and state both nonlinear. Some remarks are there. You can weaker the conditions and you can prove the results. I don't want to go into depth of this one. Practical example, x dash t equal to just scalar system. You can see over here, non-linear part I have considered sine, and that's very easy to prove. And now I would like to switch over to the infinite dimension space. Is it possible to prove to find the trajectory for the infinite dimension? Yes, it is. So let me consider w dash t equal to awt plus btut plus f of t. I just changed the notation capital F over here just to distinguish between my small f and capital F in the scalar and the infinite dimension, I mean finite and infinite dimension space. Infinite, I mean say infinite dimension space. Please guys, some pronunciations in US, they are different than India, so please forgive me. Okay. So this WT that is in the Hilbert space H and UT that is in the control space U, operator A is the infinitesimal operator from the Hilbert space H to H and not necessarily bounded. This operator B is a bounded linear operator from J cross U to H, and this G function is nothing but T and S. So J cross J, or you can say delta cross or J cross J cross H to H. F is J cross H to H. These are the system components. And my condition, my semigroup, or so I mean to say my semigroup is bounded by M1, and it satisfies this integral condition too. This one is required to make sure about the boundedness of the estimation. And my B and G, operators B and G satisfies the carry theory condition again, measurable with respect to first variable, continuous with respect to second variable. And they satisfy the growth condition, B, G, and F. All my three operators, they satisfy the growth condition, B0 plus B1 norm of U, Q0 plus Q1 norm of N, blah, blah, blah. Okay, so now I'm in a position using the assumptions 1 and 2, in a position to write the mild solution of the system using the semigroup. Infinite dimension space means semigroup, please. And let tau be the, now I just would like to give the definition of the control. Let tau be the set of all functions Z in L2 which are differentiable, and we say that the system is controllable. I'm talking about this infinite dimension space controllability, trajectory controllability. If for any Z in tau there exists L2 such that L2 function U such that the corresponding solution of my system that satisfies WD equal to ZT almost everywhere. While F is Lipschitz continuous in second and third variable, G is Lipschitz continuous in third variable, B satisfies the monotonicity. You can see strictly monotone over here. Of course, one can work with the strong monotonicity too. Here is strictly monotone, and B is a coercive operator. These things are required because here we are not using the fixed point approach. We are using over here the monotone theory approach. That's a completely different thing than the fixed point theory. There is a very standard book right now, probably it's not available, but very standard book written by Dr. Joshi and Bose, IIT Bombay. Dr. Joshi retired in 2005. Fantastic professor, very nice contribution. And he wrote one book based on the semigroup theory. Anyway, so, monotone operator theory and applications, not semigroup, sorry. Okay, guys. So ZT minus STWT, ZT minus STW0, that is equal to this one. Again, I just would like to go for the differentiation of this system. Again, I took just my control on right side, all other things on left side, just like my previous case. And finally, I wrote it down in terms of the Volterra equation again. I consider this BT equal to YTN like this. Only thing is I need to extract my UT. For finite dimension space, extraction of UT was okay. I'd use the Demlin's technique. But here in infinite dimension space, it's not that easy. It took me lots of days to fix this problem. Look at here, guys. Because of my first assumption, I can say that my operator K is bounded linear operator, and it can be easily proved that K to the power n is a contraction for sufficiently large n. That's not a big deal. And hence, by generalized contraction principle, there exists a unique solution Y such that Y0 belongs to L2. So that is okay. But main thing is I have to extract my UT for the infinite dimension space. I gave the operator n just for my nonlinear part, nonlinear functions, that is equal to BT UT is equal to NUT. Look at the technique I used over here. Because of my Lipschitz continuity and coercivity and boundedness, I say that because B is coercive, B and U, B is coercive, B is strictly monotone, and that's why N is defined continuous and bounded operator too. My second assumption says that N is monotone mapping, and that is of N is monotone mapping and coercive. Because my B is coercive, N is coercive, and it's monotone too. And every coercive mapping, a hemi-continuous monotone mapping, that is of type M. All these definitions are given in the book of Joshi and Bose, that is type M. And once it is type M, in the theorem 3.6.9 in that book of Joshi and Bose, they have proved this thing, that every nonlinear map satisfying the condition of type M that is always onto. Once we are getting onto, we are getting the exact controllability. So that's how I reach to the exact trajectory controllability in the infinite dimension space. And this is some comments are there. Let me just keep this comment. And this is another, the heat equation based on the trajectory controllability. You have to be very careful in fixing your spaces. A is the infinitesimal generator. I have defined in this form. Domain of A, that is in the Sobolev space. You are taking the practical example now. So it's a Sobolev space H2 to H01 omega. Very nice book written by Dr. Keswan. I think he is maxing at Chennai right now, or he retired probably. I met him so many times. And he wrote it down one book based on this Sobolev space. The title of the book is Sobolev space, and it's a universal accepted book. Here in United States, so many professors, they are using the book of Keswan, Kesavan. Anyway, so domain of A that is in Sobolev space like this is the domain of A, and H and U that is in L2, Hilbert space. B of T, UT, I just would like to consider U of T. And the above system is, this system is trajectory controllable under the assumptions of this one. I have considered my domain of A as a collection of all omega such that omega dash are absolutely continuous, and A omega that is in this form. This is the inner product, the omega n and omega n, and my semi-group that is in this form, that is given in this form. Semi-group that is in this form. Nonlinear operator F that is in this form. And finally, you can see over here, W dash T. If you consider this one, so this one is proved now. If you consider H equal to Hilbert space equal to Rn. So I started with scalar system, then after I jumped to infinite dimension. Now I'm infinite dimension 2, I'm jumping to Rn, means n vectors. Again, it is the finite dimension space, but n vectors. So one can go along the same line and prove the theorem for Rn also. So this new concept that is valid for scalar, R1, Rn, infinite dimension, everywhere. And that's the theorem I have proved over here. Let me just keep, this is just the example in R2, because Rn, you can take n equal to 2, 3, 4, at least more than 1, that's it. And now the trajectory controllability for second order system. Again, I'm going to use the same tool for semi-group and, cosine and sine operator, not semi-group, cosine and sine operator to get the mild solution, because cosine and sine operator can give the solution, mild solution, directly from second order to Wt without transforming to first order. So there's the advantage of making use of cosine and sine operators. So same thing I have used over here. And I would suggest to read the book of Goldstein for semi-groups of linear operators and in applications, very nicely explain the same thing. And now I just would like to give the hint about the trajectory controllability of the fractional order integral differential system in Hilbert space. You can see over here, C d to the power alpha t Wt equal to this one. This is the fractional order. Alpha lies between 0 and 1, or 1 and 2 like this. It's a fractional order. C means Kapuro derivative. So whenever you are in the fractional order system, at that time, the mild solution will not be through the general derivative. No, you need to go through some spatial derivative that is called the Riemann-Liouville derivative. But Riemann-Liouville derivative, the derivative of constant is not 0. But derivative of constant is 0 in Kapuro derivative. So that's the reason why we want to go for Kapuro derivative. So use Kapuro derivative to get the mild solution of this fractional order system. So I just gave you the definition of Riemann-Liouville functional derivative. Then this is the derivative. This is the definition, and Kapuro definition is like this. We put Riemann-Liouville. I just put RL here. Here I put C just to distinguish between these two definitions. So use this definition to get the mild solution of the system, and mild solution of the system that is given using this derivative, the fractional Riemann-Liouville problem and family that is given like this. And this is the example. This second order I have proved, this paper that was proved in that I think before 3 years, 2018, 2019, and that was published in Differential Equation and Dynamical System, Springer. So if somebody wants to refer that paper, just try to refer that DEDS, Differential Equation and Dynamical System. Okay. So consider this following nonlinear fractional order differential equation. This is a practical example. In this practical example, you can see now all this work has been done. Once I proved the trajectory controllability, then after people have started working on the fractional order too, it has been proved. And recently this one is proved. trajectory controllability of a parabolic system. This is the parabolic system. Look at over here. So now people are diverting, people like this concept, they're diverting to partial differential equation 2. You can see over here the Sobolev space, and this is the parabolic equation. But guys, keep in mind this thing. Elliptic equation and hyperbolic equation is still unsolved problem for the trajectory controllability. If somebody wants to work in this direction, it's free to work. It's not that easy. Trust me. Parabolic is okay, but elliptic and hyperbolic is too difficult. Elliptic is too difficult. Anyway, but of course, impossible is possible. You know it. So anything could happen. So that is the future. Before I start the future work, I just would like to stop sharing this one, and I would like to give you, because I have 10 more minutes to go. So let me just stop this sharing this one, and I would like to share. Where is it? Why I'm not able to share my file? I just would like to share the. Can you see this one, guys? Numerical results.
Sir, you have to change the window in sharing.
I did.
Because your sharing has not started.
Okay. Window and okay. I think now you guys are getting this one, right? Numerical results. Yes or no?
Yes, sir, it's loading.
Okay, so numerical
Yes,
results,
it is
guys.
visible.
Thank you. Now, guys, look at over here. What happens that generally optimal control problems are posed to minimize some functionals of the control function and the state variables. But unfortunately, we don't have any functional of the control or the state to minimize over here. And that's why we will pose this problem to an optimization problem constrained by the state equation. And the trajectory control U alpha, this U alpha xt is defined in this form. U alpha t equal to this one. And let me just go through and subject to this condition. So what we did, let me just go very quickly over here. What we did over here, that after we convert our trajectory, problem, whatever I described to, into discretized, continuous, unconstrained optimization problem, we can solve it using the various optimization techniques. We use two optimization routines over here. The first method, that was the Cauchy-Newton algorithm with the finite difference gradient and a line search as implemented by the MATLAB function fminUC. You can see your fminunc.m. And the second is the non-gradient method given by Nadler and Maid, which attempts to minimize the functions over the standstills of the points that is varied by the series of rules of control and the standstill size and the shape. And you can see here, guys, because of the limitation of time, it's not possible for me to show you everything, but I can just give the result. The result I'm getting over here, that is like this. The numerical solution of the integral differential trajectory control problems. On the left side, you can see I have state, control, and target before optimization. And here I have after optimization. Look at over here. This is nothing but my state xt, my blue line, and my green line, that is the control. And these red points are nothing but my target. So my target is like this, and my state variable, mild solution, moves almost along the path. Okay, and then after I got another thing, that numerical solution for the system of integral differential equation of trajectory control problem. Again, on the left side, you can see over here the state, control, and the target before optimization. Here it is after optimization. After optimization, here I have considered u1 and u2 equal to 0 just for the sake of convenience. So you can see here, this is now, this moves like this, and this moves like this. And finally, I got this estimation. You can see this. I got really fantastic result, numerical solution for the first order partial differential equation with the desired trajectory in this MATLAB form. I've used the MATLAB over here. And you can see this is my target, my partial differential equation solution that is given in blue line. And my target is given in this, this line. You can see they are just matching each other. They are just passing through exactly the same thing. Means whatever I proved theoretically, that is justified over here numerically too. And finally, the numerical solution with control found with optimization and t equal to, I just took some time interval over here, t equal to 0.444, something like this. So I just changed the time, and then after the 0.42, I just move to 0.1, I'm getting this type of problem. Look at our three-dimensional figures. So that's what I just would like to let you know, that this way one can go, one can proceed. Let me just stop this one. And again, let me go back and try to share my window for the last portion, and that is the future work. Last 3-4 minutes left out. Okay, so future work, trajectory controllability of the time and state dependent first and second order delay system. Whatever we have discussed, that was based on time dependent delay system, but there are another delay system that is called state dependent. No work has been reported so far in terms of state dependent first order, second order, fractional order, parabolic equations for finite time delay as well as finite state delay as well as infinite state delay. No, that is not reported. So that's the open problem so far. Second thing, already I told you, trajectory controllability of elliptic and hyperbolic time or state dependent delay system or inclusions are open problems too. Trajectory controllability of the fractional order dynamical system and the stochastic system with their numerical estimations. Stochastic system, I have not discussed about this last time when I was invited. I think last year at that time, I gave full lecture based on the stochastic controllability. So trajectory controllability for the stochastic system has not been done so far. So these are the open problems. I am working on this problem, but somebody wants to work in that direction. I would love to help those guys. I don't mind. That's fine. So these are the open problems in this field because there's a new notion. And now trajectory control, a fractional order dynamical system and stochastic. Now fractional and stochastic, combination of fractional and stochastic system with integral boundary condition and the integral impulsive condition. Now my condition is not just simple condition. It's not derivative. It's an integral boundary condition and impulse conditions are there in terms of integration. And so many systems in numerology, in mechanical systems, they are based on the integral boundary conditions. So that is also required. That is also one of the open things you can say. And sorry. I'm sorry, guys, just 1 minute. Okay. And finally, I have some references I just went through. I discussed about this book of Joshi and Boss, some topics in nonlinear functional analysis. And I discussed about the book of Pazzi, semigroup theory and its applications. And some of the books, I have just proved my result over here. And for the phase space book of paper of Paul and Kato and Hinomura Kaminaito. So these are the recent developments, and Trigiani, who gave a big thing based on the compactness. So I think this is my work. Thank you so much for the invite and patience hearing. I have a YouTube channel. If somebody is interested, not in mathematics, but in the spiritual line, he or she can go through my Divine Light channel. And my Dimple Chalisa, this is a channel of my education. So all the lectures, usually if I deliver a lecture, I just put this one in the YouTube. So if you have some doubts, we can be in touch via YouTube so that I can help you out to solve your doubts if it is possible for me. Thank you so much again for patience hearing, for all your support. Thank you so much. And let me just stop over here.
Thank you very much, sir.
Thank
for
you
a
very
wonderful
much, sir.
session. It is a nice session, and we have very good information from this lecture, sir. Because this
Thank you so
control
much.
theory we heard earlier, but we are not that much of clarity. Today we will get each and everything. And earlier I am also thinking about the optimization in this field. But I think conceptually I'm not that much of clear, but I'm damn sure after this lecture, sir, definitely I can go with this controllability theory and the optimization. And
So nice. I will be glad if you can do this thing.
Yes,
My
sir,
effort
yes.
will be my efforts will be satisfied if you can go through that optimization techniques.
Yes, yes.
And I know you are working in this field, so probably you can do that thing. I'm sure you can do that thing.
Yes, yes.
Yeah.
Yes,
So there
sir.
are Yeah, sorry.
Yes, sir. In such a small time period, you explained with application, like application of both analytical plus numerical method, then open problems. So that gives actually motivation to learn both both type of methods, and then again they have the open problems from your side also to work on them. So thank you so much, sir,
No
and
problem.
taking all pain to deliver lecture at such an odd time at your end.
Yeah, right
We
now
are
it
sorry
is
for
almost
that inconvenience caused.
1:45 a.m. here in United
Yes,
States.
yes.
Yeah, but Dr. Pradhan, he just sent the invite to me. I think on Sunday he sent a message to me, and I just read the message twice. I
Yeah.
thought month of September or November, October. Then I realized no, it's the September.
Yes, 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 yes. Yeah,
It's
but
okay,
next
that's
time
fine.
we'll take care and we'll inform you well in advance.
No problem. It's okay. No problem.
Yes.
Sir, was I audible? I lost my internet connection, sir. We have lots of
No,
disturbances.
it's okay. Yeah, you are audible.
Yeah,
It's okay.
Yes, yes. Yeah. Very nice to hear you, sir.
Thank you. My pleasure. Thank you so much.
Thank you. Yeah. Okay. Okay, thank you so much.
Okay, guys. Thank you. Thank you so much.
Okay, thank
Okay.
you.
Thank you,
Again,
sir.
thanks
Thank
for
you
the
very much,
invite.
sir.
Yeah.
Yeah,
Thank you.
thank you.
Take care.
Thank you, sir.
Thank you,
sir.
Yeah. Good
Yeah,
night. Good night
Doctor.
from our end.
Yes,
Thank you.
sir. Good night, sir.
Thank you. And Saroj Yadav, you are the organizer of this conference, right? You took the initiative.
Yes.
Very
Yes,
nice.
sir. Yes, sir. With
So
the
nice.
guidance, under the guidance of Pradhan,
Dr.
sir,
Pradhan
and
and
yes,
yes,
sir, Jay, sir.
Pradhan and Dr. Jayesh, sir. Yes.
Yes, sir.
Yes.
Yeah.
Yes.
So you have a nice group. Yes, you guys can do really good.
Yes.
things.
Yes.
Yeah.
Okay.
I'm just thinking maybe I can visit in December or otherwise in the month of.
Yeah.
next
Most
October,
welcome.
like this.
Most welcome, sir.
You are welcome.
Most-
You are always welcome here, sir.
But definitely, I will try to see you at the time.
Sure. Definitely. Yeah.
Okay, sir.
Okay. Fine. Yeah.
Okay,
See you
guys.
again, sir. Yeah.
Thank you. Thank you so much.
Bye, sir.
Thank you, sir. Thank you very much, sir.
Good night, sir.
Good night.
Bye.
Good night. Good night. So, all participants are requested. We'll our next session, that is at 2 o'clock. So all are requested to reach at the 2 o'clock.
Yes, sir. And one more instruction. Please join meeting on time. I will insist join before 5 minutes. Always join early. And prerequisite for the lecture we will have from 3 p.m. onwards. We need Matlet. So if you want to try with the speaker, if you want to try it on your device too, so download Matlet. You may go for some free trial version and have Matlet with you. Thank you all. Thank you, sir.
Thank you, sir. Thank you very much, sir. Thank you.
Thank you.
Thank you.
Yeah. Dr. Saroj.
Yes, sir. Yes, sir.
Every day's schedule you displayed.
Yes, sir. I sent it to all participants.
Have you sent it to all the participants?
Yes, sir.
Yeah, fine.
Yes, sir.
Okay.
So from tomorrow onwards, we will have our first session at 10 a.m. in morning.
Okay, fine. Okay. Thank you.
Okay,
Now
sir.
you can stop the recording if the
Yes,
program is over.
Yes, sir. Yes.
Yeah.